The population is the collection of all the outcomes, responses, or measures, whereas the sample is just some subset of the population. So if here we had everyone, so that might be something like the US population. And then we did a survey where we talked to some group of 1,000 Americans. So this would be our population. And then the specific people we talked to would be our sample. Let's look at another example. In this example, it tells us that there's a survey of 1,500 adults in the US, and they were asked if they thought that there was solid evidence of global warming, and we had 855 adults say yes. So we want to identify the population and the sample. So the sample is just the people we talked to, so it's just the 1,500 US adults. But since we only surveyed US adults, we must be interested in only US adults as our population. Okay. And again, this sample is a subset or some smaller group of the bigger population. The data is our list of yeses and nos. Specifically, since it tells us that 855 say yes, that means it is a list of 855 yeses, and the remaining 645 people would have said no. A parameter describes a population. For example, it would be the average age of all the people in the United States if everyone was our population. A statistic goes to a sample characteristic, like the average age of the people in some 3 states instead of all 50. So parameters describe populations and statistics describe samples. I have a nice little alliteration there to help you remember which goes to which. Now we want to use what we've learned about population parameters and sample statistics and apply it to some specific examples. So in number 1, we've got that a recent survey of a sample of college career centers reported the average salary for petroleum engineers at $83,121. So since it's got this word sample and the survey also implies we're talking about a sample, that means we are talking about a sample statistic, right? Because that doesn't apply to all petroleum engineers, just the ones in our sample. Question 2, it says the 2,182 students who accepted admission offers to Northwestern in 2009 have an SAT score of 1442. So that means we are talking about a population because this is all of the students who accepted admission offers. So the entire population being students who accepted admission offers to Northwestern University in 2009 would make this that population parameter. There are several different branches of statistics. First is descriptive statistics, which is about organizing and summarizing and displaying the data. So it's just showing you the numbers. There's no manipulation. It's just the numbers. It's things like tables and charts and averages. Inferential statistics are taking this data and then drawing some type of conclusion about the population. So we look at our sample, the few people we talked to, and we know what things look like for them, but in inferential statistics we take that information and try and make some type of statement about the wider population and not just those in our sample. So in this example, we want to determine the difference between descriptive and inferential statistics. So we've got a large sample of men, age 48, studied for 18 years. For unmarried men, approximately 70% were living at age 65, and for married, 90% were living at age 65. So this information right here, this is the descriptive, right? It's just the facts. But as you read this, or listened to me read it, you probably thought, the married men were more likely to live longer. That is the inference. So the inference is the conclusion we draw from the data. And so in our sample, it was definitely true, but there's a good indication that a married man might live longer, or at least they're more likely to live longer. It's not a given, but it's one of the factors. So there's two types of data. First are qualitative data, and these are just attributes or labels. They don't have any type of numbers, or if they're numbers, they aren't meaningful numbers. So something like a major, or a place of birth, or an eye color. Right? All of those are words or categories. Whereas with qualitative data, these are numerical measures. So things like an age, that's a number, the weight of a letter is a number, and a temperature is also a number. So here we have two columns, one the model of a car, and the second the retail price. And we want to separate which column is qualitative and which is quantitative. So remember, qualitative lists qualities and quantitative lists quantities. It's where they get their names. So quantities are numbers, which we have over here, whereas qualities are more like words or descriptor categories, which is what we have in the left column. So the model would be qualitative and the price would be quantitative. There are 4 different levels of measurement, and each one allows you to do more with the numbers that fit in that category. So the lowest level is called nominal, and nominal is only qualitative. So that means it's only those qualities. It's like eye color and location. And with these, you can't do any mathematical computation. The next step up is ordinal. And ordinal can be either qualitative or quantitative, but the key difference is that ordinal data can be arranged in some type of order. So the differences between these data entries shouldn't be meaningful, but being listed first should be different than listed second, and that order should be meaningful. The next highest is interval. So these data are qualitative and only qualitative, and they can be ordered. And here the differences between the two also mean something. So being 2 spaces up actually has some meaning. But here a 0 is not a true 0, meaning it doesn't mean nothing at this point. And the ratio level is everything that interval has, except that 0 does actually mean none. And because of that, one value can be expressed as a multiple of the other. Now let's look at an example where we classify the different kinds. So let's look at our first one. First, we have this list of home runs. So focusing on the home run list itself, we see we have numbers. So we're going to be talking about one of the higher levels. And so we need to ask ourselves, could we order these things? And in fact, we could. We could order them by the lowest number of home runs to the highest number. So that gets us at least to the ordinal level. Then the nominal says, does differences have meanings? Well, if we looked at Baltimore versus Boston, which has a difference of 52, it does have a meaning. Boston had 52 more home runs than Baltimore. So it's at least at that level. So let's check the next highest. That one is that 0 means 0. And since here 0 means no home runs, that means we must be at the highest level of ratio. Let's look at another example. Here we have a list of network affiliates. So we don't have numbers, so we're not talking about the last two, but we could be talking about either of the first. And specifically, we see here that the different ones are just letters, and that these letters have no order other than maybe alphabetical, but that's not a meaningful order, and so we must be talking about nominal. Next, we have a ranking of the top 5 TV programs. And since these are words, we know we're talking about one of the lower 2 levels and not the upper 2. But here, being first is different than being second. So since these have ranking meanings, they must be ordinal. And then lastly, we have the lists of the years that the New York Yankees won the World Series. We can see that the lowest, or that the different years are numbers, so that means we're talking about any of the top 3. In fact, we can rank them, right, from the earliest to the most recent, and a difference between 1923 and 1927 has meaning, 4 years between those 2 victories. So we've moved up to at least the interval level. And last to see, does 0 mean 0? Well, the year 0 was not the beginning of time. When that happened may be argued across people, but no one thinks it's what we call year 0. And so, since this is not an inherent 0, this is interval data. One method of collecting data is using an observational study. And in an observational study, the researcher just watches and then takes note of what happens. So for example, if researchers were to observe and record the mouthing behaviors on non-food objects of children up to 3, so basically they're watching to see what all children teeth on and how much they teeth, and then they take note. So they're just watching the children. An experiment is when you actually apply a treatment to some part of your population you're looking at. So for example, an experiment where you look at the impact of cinnamon on diabetics, where you have a control group where some take no cinnamon pills, and then another group that does, and then after 40 days you look to see who has a lower risk of heart disease, and see if that's different than just your control group. So that's an experiment. You're giving some people a pill and seeing what happens. A simulation uses a mathematical or physical model to reproduce the conditions of some type of situation. And this is often done with computers. So for example, automobile manufacturers use simulations with dummies in order to estimate the effect of a crash on humans. Now, that is called a simulation because they're making the accidents happen. They often also do it on their computer to have an idea before they even build the car to know how safe it's going to be. This happens with buildings as well. So anytime if you were to do this as an experiment instead of a simulation, if it's going to likely cause death or injury, a simulation is usually what's going to be used, because then you're just talking about simulated death and injury. And a survey is when you look into one or more characteristics and you write up some survey questions, usually on a phone or paper interview, and you ask your questions you're interested in and just catalog the responses. For example, a survey could be conducted on some sample of female physicians to determine whether the primary reason for their career choice is financial stability. So you're calling them up and you're asking them what their primary choices were, and then taking that information to see if you can draw some inference. A large focus of this section is on experimental design. So about how to construct a different experiment so that you have the least possible amount of bias. So make sure you read all those different ways about control groups and placebos and strata and all of that to make sure you understand. But I have an example here, and we want to look at a possible problem with how they've done this. So we've got a company who wants to test the effectiveness of a new gum to help people quit smoking. And we're going to try and identify a problem and give a way to improve it. So the company identifies 1,000 adults who are heavy smokers. The subjects are divided into blocks according to gender. Females are given the new gum, males are given the placebo. After 2 months, the female group has significant numbers of subjects who have quit smoking. So the problem we have is that one gender is given one thing and another gender another. Now it's possible there's some gender bias, that when females know that they're supposed to quit smoking, maybe they're more likely, and that the gum wasn't the important part. So what would be better is to, once you split the males and females, take the females and give 50% the placebo and give 50% the active gum. And then with males, do the same thing. Put half of them in the placebo group and half of them in the active gum group. So that way you can see if there is some type of gender bias. Now you may want to create blocks on other possible categories like age or length of time they've been smoking, but the big problem with this is not splitting up by gender. So now we want to see if we can identify the sampling technique being used. Okay. So we're looking at the opinion of students regarding stem cell research. So the first option is to divide the student population with respect to their majors and randomly select and question some students in each major. The idea here being that the religion and biology department are probably, or may very well have, different opinions on the topic. So here we are separating the different students by major into something we call strata. And so that means we are using the stratified sampling method because we're separating by group and selecting a few people from each group. Another option is to assign each student a number and generate random numbers. And then whoever's number is generated is who we talk to. So this is a very basic random sample, and so we call this method the simple random sample. First, I'm going to talk through the process of constructing a frequency distribution, and then I will work through a problem doing that. So first, you've got to decide on the number of classes. This is going to be given to you in your problem, so you just look for the number of classes in the problem. Usually it's going to be between 5 and 20, otherwise it might be too small or large to really tell a meaningful pattern. Then you're going to find the class width. And you do this by finding the range of the data, so you take the largest one and subtract the smallest one, and you take that range that you get out, divide it by the number of classes, and then round up. We always round up, and that will give you your class width. If we round down, then we might not include as many numbers as we need. So then you find your class limits, and the first class limit, the lower one, is your minimum data entry. So the smallest number of all your data points is where you start. Then you're going to add the class width to that lower limit to get your next lower limit, and then add it again to get the next one. You continue till you reach your last class. And then to get the upper limit of that class, it is the number before the next class's lower limit. Sounds complicated, but it's actually not too difficult to do. Then once you've got all the classes determined, you look back at your original data and you make a tally mark for each class whenever you see that data. And then you count the total tally marks to get the frequency for each of the classes. So we're going to be working through this list of 30 GPS prices and construct a frequency histogram with 7 classes. So first we need to find our cheapest one, which is the $59 one right there. And then we need to find our most expensive one, the $450 here. So to find the class width, we take the range, which is the biggest and most expensive one, subtract out the cheapest one, and divide it by the class width, or the number of classes of 7. So 450 minus 59 is 391 divided by 7 gives 55.86. But remember, we round up, so that means 56 is our class width. Remember, 59 was our cheapest of our GPSs, and so that starts it off. Then we add our class width of 56 to get 115. And then we add it again. We add 56 to the 115 to get 171. Add 56 again, 227, and again 283, and again 339, and then for our 7th class, 395. To get the upper limits, it's just the one before. So this is 115, so that means the previous one must be stopping at 114. And if that's 171, this one must be stopping at 170. And then 226, 282, 338, 394, and now I can't do my process. But these are also 56 apart. So that means I can add 56 here, get 450, and that fills out my last one. So now that we've found the class limits, it's time for the tally marks. So I just go through my data one by one and figure out where they go. So first I have 90, and 90 is between 59 and 114, so I put a tally mark there. And then I have 130, which is in that range, 400, which is in this bottom range, 200, 350, 70, 325, 250, 150, 250 again, 275, 270, 150, 130, 59, 200, 160, 450, 300, 130, 220, 100, 200, 400, 200, 250, 95, 180, 170, and 150. And so that comes to 5, 8, 6, 5, 2, 1, and 3. What we just found in the table was the frequency. We can find the relative frequency, which says relative to our entire sample, how much is in this class range. So you take your frequency that you just calculated, divided by the total number, and that'll give you the relative frequency. The cumulative frequency is just the sum of all the previous frequencies. So it's how many are up to that point. So now let's add those to our table. I did not mention midpoint on its own slide, but we can cover it here briefly. So the midpoint is just the average of these class widths. So for the first one, it's the average of 59 and 114. So 59 plus 114 divided by 2, and that gives you 86.5. And then for the next one, it's 115 plus 170 divided by 2, which gives us 142.5. And continuing that process, finding the average of the two endpoints for the given class will give you the rest of these numbers. And lastly, okay. So now the relative frequency is just our f divided by our n. And so it told us originally that there are a total of 30 GPSs, and if I added up those 7 numbers, I would get 30 as well. So that means for our first category, we have 5 out of 30, or 1/6, and that comes to 0.17 if I round to 2 decimal places. For the next category, we've got 8 out of 30, which rounds to 0.27. Then 6 out of 30, which is exactly 0.2. 5 out of 30, which is 0.17. 2 out of 30, because again, we've got the 2 over there. That's how we're getting it. So the 2 out of 30 is 0.07. The 1 out of 30 is 0.03. And 3 out of 30 is exactly 0.1. And so if you add up all those relative frequencies, you will get 1 for the total. So the cumulative frequency is just the frequency of the category you're at and all the others added together. So for our first class, there are no previouses, so the cumulative frequency is just 5. For the next class, it's the 8 plus the 5. So that's a total of 13. Now for this one, we're adding 6 to our previous total, getting us 19. Then we add 5 to our previous total, giving us 24. Add 2, giving us 26. Add 1 for 27, and 3 to get to 30. So the cumulative frequency, your last class should have the total number of all things, which for this, it is 30. Bar graphs are used to represent the frequency histogram. You can see an example down in the bottom right corner. And so on the horizontal scale, down here, we use the data values, and the vertical scale is the frequency. And with these in a histogram, your consecutive bars must touch. So from our previous example, we found the class boundaries and the frequencies, but we just said that we can't have gaps for our histogram. But we do, because we go from 114 to 115. There's a gap there. So we find the total distance between those two by subtracting them, and we get 1. So we want to split that distance. So 1 divided by 2 is a half. And we split the difference by subtracting it from the lower boundary and adding it to the upper. But you do that for each of the classes. And so when you do it, you get this middle column. And you can see now they match up. Right? So there are no more gaps. So we can create a histogram of our information. Here are 2 examples of a frequency histogram for the data we've been working with. The difference is how the bottom axis is labeled. You can see one labels the midpoint and the other labels the bounds of the bar. And so in the second graph, we can see easily that more than half of the GPS navigators are below the price of $2.26. Because if we were to draw a line right here, it shows us that. So that's one advantage of using the class boundaries. By using the midpoints, we can easily have a way to know the middle of that column, so an easy way to refer to it. A relative frequency histogram is the same, only it has the relative frequency on this axis. So notice these numbers are decimals instead of being the whole numbers. And so when you report it like this, you're able to see that between $114 and $170, so this bar right here, we can go up and read and see that about 27% of GPS navigators are in that range. A Pareto chart looks similar to a histogram, only it's not just for qualitative data, or quantitative, excuse me. It can also be for qualities. So here in this example, we have listed 4 main reasons for inventory shrinkage. And in our Pareto chart on the right, it lists them from the largest to the smallest. That's one of the qualifications to be a Pareto chart. So it's very handy. You can easily look at this and see that employee theft is the largest problem, followed fairly closely with shoplifting. And those other issues like vendor fraud and administrative error are fairly small in comparison to the first two. A scatter plot, as you see in this example, shows how variations in one variable gives variations in the other. So we have petal length down here and petal width referring to flower petals. This is actual data that was collected. And you can see that as the petal length goes up, so does the width. So we're able to make some assumptions about how a longer length usually means a wider width as well. There are 3 main measures of central tendency. First, you have the mean, or the average, and that is just the sum of all the data entries divided by the number of entries. And it looks like that for the population and this for the sample. Notice the new notation. This mu here, it's a Greek letter, it's called mu, is the population mean, whereas the x with the line on top, usually called x bar, is the sample mean. So this refers to a parameter, and this one is a statistic. The difference between these two notations is actually going to be very important for the rest of the course. The next measure of central tendency is the median. And whenever you order the data from least to greatest, the median is the one that is in the middle. If there's an odd number of things, then you will have a middle entry left. However, if there's an even number, you'd have 2 things in the middle. And so you just find the average of the 2 things in the event that there are 2. The mode is the third one, and that is the entry that occurs with the most frequency. So mode means most. And it's possible for a data set to have one mode, it could have multiple modes, or it could have no modes, depending on the number of occurrences. So to make these calculations easier, I'm going to use Excel. You can see that I've already got the numbers entered. Right? If you need help learning to do basic things like entering numbers in Excel, please see the module page called Excel Basics. It's got several videos to help you get more accustomed with how to use Excel. So one of the really useful things it does is its functions. So we want to find the measures of central tendency. The first one is the mean, or the average. So if I typed an equal sign so that Excel knows that I'm going to give it a formula, and then I type the word average, like I have now, and then a parentheses, you see down here Excel will pop up some hints as to what it's looking for. So I did equal average parenthesis, and then I'm going to click and hold my left button to select all of them. Close my parentheses and push enter. And so that will give me the average price. Now it also does the median. So equal median, and then I'm sure I won't select my mean, so I stop where I did before, clicking and holding, closing my parentheses, and I get my median of 427. And then we also want the mode. And so I click and hold, push enter, and I get that 397 occurs the most. Now this will also do, okay, apparently it will not do the range, I apologize. So for the range, I'm going to have to look for my biggest number, which is this cell. I could type 872, or I can click on it. Again, I started with an equal sign so that Excel knows I'm giving it a formula. So I want the biggest one, and then I want to subtract out the smallest one, the 388. And that, when I push enter, will give me my range. So if you want to see those formulas again, that shows you what I typed to be able to get the median, mean, and mode. So the population variance, we use sigma squared, it's also a Greek letter, to represent it. And you find how much each entry x deviates from the mean, square those deviations, and add them up for each of the x's, and divide by the total number. For the sample, you do the same thing, except that you divide by n minus 1. Now this is because a sample is not as precise as a population estimate. So we've got to take some countermeasures, and that's what this denominator does. And we call a sample variance S. Now, for the standard deviations, in both cases it's just the square root of the variance, and these numbers are what we're going to talk about a lot. Because variances are in squared units, so that's something like if we were talking about the number of days someone comes to work. So the variance would be talking about days squared. Well, I don't really know what a square day is, but I do know what a day is. And so that's what we have down here with standard deviation. So we're going to use that more. The variance is really just a step to get there. All right, I know these formulas look complicated, but we're going to let Excel in an example do all the heavy lifting for us. This question gives me 10 different salaries and asks to find the standard deviation and variance. So since these 10 salaries are all 10 new employees, not just a sample of new employees, that means we are talking about a population. And since we're talking about a population, our formulas are different than if we were talking about a sample. So I want you to remember that. So if we want to find the variance and the standard deviation, we'll use the following formulas. So equals variance. And since we're talking about a population, and I can see 2 pop up here, but I'm talking about a population, so it is the variance P. And I double clicked, and it made it to where all I need to do is click that, close my parentheses, and it gives me my population variance. And the same goes for the standard deviation. So I've got a P and an S, but this is a population. So I double click on it, and then I click and hold to be able to get the rest, and I get that one. Now, if it was talking about a sample, this question is not, but if it was, then I would use my variance.s formula. If I double click, it pops like that. You also can just continue typing. And for the sample, standard deviation, it's the .s again, and that comes to that. So you can see that the sample has larger numbers. Again, that's because it's adjusting for the fact that it's only a few members of our population instead of the entire one. So it's adjusting for that. So I'll show you my formulas again. Let me compact that so you can see, depending on if it is a sample or a population, as to which formula you use. So standard deviation is more important than just because it's in a unit we know how to use. The standard deviation is the measure of a typical amount that an entry may deviate from the mean. So let's look at an example here. All three of these pictures have an average of 5. In the first one, there is no deviation. Everything is right at 5. In the next one, we see we've got a little bit bigger of a deviation. It goes up to 1.2. So they're spread out a little more. And then in the third and final one, we have a yet bigger standard deviation of 3, where we see no actual entry is at 5. They're away from it, and they're very spread out. So as our standard deviation goes up, the spread gets further and further out. Quartiles are whenever you divide an ordered set of data into 4 equal parts. So that means you take your data, you list it from the smallest to the largest value, and then you split it into 4 equal parts. Your first quartile is the first or bottom 25% of your data. The second is the bottom half of your data, so it's your median. And the third is the top 3/4. The interquartile range is just your Q3 minus your Q1. So the process that you would find quartiles is first you find the median. So you order your data and then you find the one that's in the middle. And then once you find your median, you split into your lower and your upper halves, and you find your median of your lower half and your median of your upper half, and that'll give you your first and third quartiles. So below we have the number of nuclear power plants at the top 15 nuclear power producing countries in the world. And we want to find the 5-number summary and the IQR. So the 5-number summary is the minimum, the Q1, the Q2, the Q3, and the maximum. So first we're going to have to order these data. My smallest number is 6. My next smallest number is 7. And then I've got an 8, and then a 10, an 11, a 15, a 17, an 18, another 18, a 19, a 20, 31, 54, 59, and a 104. Okay, so now that I want to find the median, I'm going to switch pen colors, and I'm going to start from the edges, marking them off one side at a time till I get to the middle. And so my median, or my Q2, is 18. I also have that my minimum is 6, and my maximum is 104. Okay. So now that this 18 has been deemed the median, it is not a part of the bottom or the top. Now if I had averaged to get it, then that means it would be, each of those parts would be part of it. But since this is a median, it's Q2 all on its own, I'm going to not use it. So using the same process in the lower half, marking off the edges, I'm left here with a 10 in the middle to give me my Q1. And then I do the same thing in the top, marking off one at a time, and that gives me my Q3. And so the IQR is Q3 minus Q1, so 31 minus 10, which gives 21. The standard score, or z-score, represents the number of standard deviations a certain value is away from the mean. So it tells us how far away from our average or our middle it is. So we use this formula where we take our value, subtract out the mean, and divide by the standard deviation. So in this example, it gives us some information about Heath Ledger's Best Supporting Actor win and Penelope Cruz Best Supporting Actress win. And we want to see if either actor or actress was more away from the normal age than the other. So we have that Heath Ledger won the Best Supporting Actor at age 29 for his role in Dark Knight, while Penelope Cruz won for Best Actress at age 34. We also know that the average age of all actor winners is 49.3, or 5, with a standard deviation of 13.8. And Best Supporting Actress winners is an average of 39.9 with a standard deviation of 14.4. So since these two awards have very different averages, their standard deviation is not too different, but their average is very different, we're going to need to convert these to Z's in order to see who was more away from average. So let's work on Heath Ledger first. So we take his age of 29, subtract out the average of 49.5, divide by the standard deviation of 13.8, and we get that he is 1.49, a negative 1.49 standard deviations. So that means he is almost 1.5 standard deviations below average. Now let's try Penelope. So she was 34 when she won her award. Actresses are on average 39.9 with a deviation of 14.0. So when you subtract and divide, you get a negative 0.42. So while both of these actors and actresses were below average, we can see that Heath Ledger was more below average by being 1.5 standard deviations away instead of just about a half. So Heath Ledger's award was further from normal than Penelope Cruz's.